Hello, this is Jixel Johnson from ENGI 1331, Dr. Kota's 10 a.m. class. So we did the chemical processing project. So basically how this project works is an ammonia plant. So the way the ammonia plant works is that you pump some nitrogen and you pump some hydrogen and 3 nitrogen for each hydrogen because it's NH3. So the way that we pump it into a reactor and we condense the nitrogen and hydrogen and the ammonia off and the nitrogen and hydrogen since they have a lower dew point and they're condensed. So we're able to reconnect and recycle most of the nitrogen hydrogen while some of it doesn't have to be purged. So according to task 1, we were asked to determine the composition of each stream in terms of the mole fraction of the inert gas in the fresh feed, which is X naught, and the fractional conversion of the reactor, which is FSP, and the fraction of gas leaving the reactor, which is YP. And these were all given in the chart. So how we found NR, NP, and FV, which is the total moles fed into the reactor and the moles of ammonia produced, which is NP, and the fraction of overall nitrogen conversion, which is FOV, is with this basis that the input equals output. So we found that 4n1 plus n2 is equal to 4n1 plus 1 times 1 minus yp times 1 minus fsp plus n2 plus 1 minus yp. And we also found that xi naught is also equal to yp times n2. So we put the n1 equation in terms of n2 so we can find each of them with two unknown variables. So the next thing that we did was create a function with all the known inputs. So we were given all these inputs and we calculated n2 and n1 and we called a function ammonium and we calculated nr, which is the total number of moles, using the equation that 4 times n1 time plus n2 and np is equal to 2 times fsp times n1. And FOV is 1 minus x naught divided by 4 minus yp times 1 minus fsp times n1, all divided by 1 minus x naught divided by 4. So if you run task 1 with running the function, we enter the mole of inert gas, which in the test case is 0.2, fractional conversion of the reactor 0.1, and the fraction of gas leaving the reactor, which is 0.005. So, sorry. So the total moles fed into the reactor, which is NR, is calculated to be 47 moles, and the moles of ammonia produced totally, which is going to be 0.383 initially, and the fraction of overall nitrogen conversion is 0.957. For task 2, we are asked to graph and analyze the system to compare YP with NP, NP with FSP, and NP with X naught in the system. So for the first one, it asks us to keep X naught and FSP constant, and we're keeping this commented because X naught and FSP were already established in task 1, so we're not clearing the workspace, so it's gonna be pulled from the workspace. So then we created the YP, which was from 0.01 in increments of 1, 0.01 to 1, which is a 1 by 100 matrix, and NP is an empty matrix initially because we want to get a new value for NP every time the YP runs in the for loop. So the loop was created to get all the x values from 0.01 to 1 and the respective y value that goes along with that x value. So initially, then we calculated n2 and n1 using the equation in task 1 to get NP using 2 equals FSP times n1. Then we calculated NP, which is initially 0, and this new NP is a new value. So every time it runs, it adds to the value, creating a 1 by 100 matrix, which helps it graph later on. So basically the reason for the loop is that yp is a vector that has 100 values in it. The loop calculates np at every value of yp to create a 100 value vector. Then we were asked to graph the function. So we graphed yp versus np. So we use the polyfit function of exponential fit to do log10 of both of them to get the slope and the y-intercept using xfit from 0.01 to 0.01 to 1. And we didn't want to hard code it, so we did axis is equal to the minimum of yp and the maximum of np. So for the second one, it asked us to keep x0 and yp constant, which is the same process as before, and fsp goes from increments of 1.1 from 0.1 to 1. And it's the same process as keeping np to find np for 100 matrix vectors. So we have a fsp in the for loop going from 0.01 to 1, calculating n2 and n1, getting a new value of np, putting it right next to the old value of np, creating a 1 by 100 matrix, and proper plotting over here, and linear fitting the polyfit, which was a linear function, and fsp and np, getting the slope and the y-intercept. And lastly, it asked us to keep fsp and yp constant. fsp and yp is already established in the workspace, so we do not have to re-establish a user input. So x naught goes from 0.01 in increments of 0.01 to 0.99. So the same process, the loop was created for all the x values from 0.01 to 1 and the respective y value that goes along with that x value. So np was calculated using 2fsp.n1, and a new value of np would be right next to the old value of np. To graph the third one, we're using polyfit to get the linear equation of x0 and np3, using linear fit of x0 and np3 and calculating the slope and the y-intercept and putting it in y-intercept form. So if we were to run this task 1 and task 2 together, it asks us for the inert gas, 0.2, 0.1, leaving the reactor, 0.5. So as you can see, it calculates all of the polyfits of the three graphs. So this is figure 3, which is a linear fit that's downward sloping. Next one is figure 2, which is FSP versus NP, and YP versus NP. As you can see the relationship on the command window. As YP increases and NP decreases at an exponential rate for figure 1, as FSP increases, NP decreases at an exponential rate for figure 2. As x0 increases, the yp decreases linearly on figure 3. So going over to task 3, it asks us to optimize the system based from observations from graphs 2 in task 2. So from looking at the graph, we came to the conclusion that yp needs to be 0.1 and fsp needs to be 1 and x0 needs to be 0.01 in order to maximize the ammonia. So if we were to look at the yp graph, we can see that when yp is 0.01, the NP, the production of ammonia, is at the maximum, which is around above 0.35. So if we were to look at the FSP, we can say that when FSP is 1, the production of ammonia, NP, is at the maximum at this point. And when we look at the X naught equation, we can see that when its X naught is 0.01 at this location, NP is at the maximum. So we can calculate N1 and N2 using the same equation from task 1. And in order to optimize the production of ammonia, we are setting the X0, which is the mole fraction of inert gas, in the fresh feed to 0.1, because the graph shows us that when X0 is at 0.1, the other two variables are held constant. Ammonia production is at the greatest at this moment. We decided that yp is the minimum because yp is at 0.1. The production of ammonia is at the greatest because of the graphs we created previously. And we're calling a function ammonia and resulting in NP, which is the molar mass. And we're printing the theoretical production of ammonia. So finally on task 4, which asks you to find the utility cost to condense the ammonia, would ask you to have a user input of NIN, which is the total molar inlet flow rate, which is given in kilomoles per hour, which you have to convert to moles, which you have to multiply by 1,000. And you have to get the X naught FSP and YP, which is the mole fraction of the inert gas, the fractional conversion of the reactor, and the fraction of gas leaving the reactor. And just as in task 1, you have to calculate N2 and N1 using the chart. And we created a cost function to calculate the total amount to condense the ammonia. If you go to the cost function, we're calling the function and we're calculating the number of moles for every single one of the N2s, H2 and I, and NH3 total. So joule, the equation for joule is going to be Q equals NCAT. So N is going to be the number of moles, which is going to be 1 minus FSP times N1, which in this case is proven by, so moles of N2 is going to be 1 minus FSP, and moles of H2 is going to be 1 minus FST times 3N1, and moles of I is going to be N2, and mole of NH3 is going to be 2 FSP N1. So as you can see, I'm multiplying the number of the heat capacity 29.1 of N2 times the temperature difference times the moles. And for H2, I'm multiplying the heat capacity 28.6 times the difference of the temperature times the moles. And for the inert gas, I'm multiplying the heat capacity 20.7 times the heat difference times N2, which is the moles. And for NH3, its Q equals MCAS is going to be 41.4 is heat capacity times the temperature difference times the heat of vaporization. The addition of the heat of vaporization, which you have to multiply by 1,000 because it's given in kilojoules per mole. And you have to get it in joules, so you have to multiply by 1,000 to get in joules. Plus the heat capacity times the molar rate times the moles of ammonia. So why you gotta do this is because you have to take into account the heat of vaporization that is going through the ammonia, and you have to multiply the whole thing by the number of moles as I have done so. And I added them all. I added all the joules of H2, N2, and I and H3 together, and divided it by 10 to the negative 6 to convert joules to megajoules. Then I multiplied by 17.38, which is the cost per megajoule, and which came out to be a negative number, but you had to get the absolute value of the number. And when you run that function, NIN is 2.2.1.005, and the total cost would be 1.46 times 10 to the fourth. And I have created a while loop to ask the user if they want to repeat the function, and if it's a yes, and it's a menu. If it's a yes, it'll go out of the loop, and it will go out of the if statement and go back to the loop. If it's a no, it will change the condition for the while loop and will exit the while loop. So if I put yes, it will rerun. So 3.2.1.005. As you can see, the cost changes, and if the user does not want to repeat the function, it goes out of the loop. Next, we can test the code using different inputs. So if I were to run this code from the beginning, 0.09, 0.01, 0.006. So as you can see, the graphs arrange accordingly, and the total moles of ammonia and the ammonia produced and the nitrogen conversion is changed accordingly. And if you go through the next task, for task 3, which is optimizing the equation of the ammonia production, we can see that ammonia is calculated in the command window. And task 4, it asks us to find the utility cost to condense the ammonia. If I were to run this section, enter the flow rate, anything but 1 mole of inert gas. As you can see, the total cost of cooling the gas is outputted in the command window. Limitation in this code, as you may have noticed, is that the beginning of the mole fraction can only be a smaller and smaller amount. So we had to start at an amount like 0.1 and increase by increments of 0.01 to 1. And we also had to input a given to create a graph and set an amount of data in the plots, which is inefficient. Also, as a conversion through the code might not be as efficient as it can be, as we have the same line of code that could be set outside, but were left where they were, as it were easier to understand. So the efficiency is not as high as it should be. Also, an engineer can use this to input the amount of material they need or they have and graph it and then determine what maximizes and minimizes it and then code accordingly to the desired result. This code can be extremely useful if you're dealing with chemicals and want to know what maximizes and minimizes the production of any chemical that you need. Thank you, and that is it.